All right, so let's go ahead and get started today. So we got quite a bit to talk about. It's probably going to be on the long side as far as a lecture today. And then there's also an activity, and then after that, you'll have the rest of the time to work on lab work. I would imagine most of you are still working on lab 4, and remember that's due after the midterm on Thursday. It's due this Friday. And then after the lecture, there's a small part of lab 5 you could do, but again, lab 4 should be the priority. So even though today's lecture is going to be, I think, on the long side, after the midterm on Thursday, that lecture should be relatively short. And after that lecture on Thursday, after the midterm, you should be able to do lab 5. But lab 5 is not going to be due until the end of next week. So, so again, just to give you an idea of where we're at and where we're going, that sort of thing. So anyway, you can see there's quite a bit on the agenda. Today we're going to start talking about circuits that have memory. Okay, and circuits that have memory are called sequential circuits. But I want to start with something we've already talked about, and that's combinational or combinatorial circuits. Okay, and again, like we said before, when you have a combinational circuit, and that's everything, all the digital logic circuitry that we looked at prior to today. And we already talked about the 2 things that combinational circuits don't have. So what are those 2 things? Right, memory. That's what we're going to start talking about today. Doesn't have memory. And what's the other thing that a combinational circuit doesn't have? What's that? Select. Well, a select is if you're referring to the select input of the mux, a mux is a combination. So we can have an input that does the select those. Remember what the other thing is? It goes right. Well, we're going to see a latch is the circuit that's able to store data. So that is like a main component of memory. Clock. Yeah, it's a clock. You'll see what a clock is today if you don't already know, as far as what it means in digital circuits. But yeah, if you don't have memory in a logic circuit, you don't need this thing called a clock, okay, which is a type of signal. Okay, now also, if you have combinational and combinatorial logic circuitry, another feature that we haven't talked about yet is that the output of this type of circuit only depends on, so solely depends on input. Okay, so if you have a combinational, combinatorial, again, it means the same thing. Whatever your output is, that output is only going to depend on inputs. Okay, you're going to see a sequential circuit has a different dependency. Also, before we talk about sequential circuits, I also just want to remind you of the NAND gate, because you're going to see we're going to have a circuit that has a NAND gate. So do you remember the truth table for a NAND gate? 1, 1, 1. Yeah, you only get a 0 out and all inputs are 1, right? But remember the NAND gate is an AND with an inverter on the output, right? So the way I remember is, I know an AND will only give me a 1 out when all inputs are 1. And then I just remember, well, an AND is just an AND with the output inverted. So an AND, you only get a 0 out when all inputs are 1. Okay, that's my thought process. Maybe you have a different one. But I think that's better than just trying to rote memory, because a lot of time when you try rote memory, it's easy to get something wrong. But anyway, that's the truth table of an AND, right? You only get a 0 out when all the inputs are 1. Otherwise, the output's going to be a 1. Okay, so this has all been pretty much what we talked about before. The only thing again that's new here is that, again, a feature of a combinational circuit is that the output just depends on inputs. All right, but now sequential circuits, Well, sequential circuits do have memory. And they do have a clock. Also, sequential circuitry, the output depends on not only inputs, but also outputs. So here's a block diagram of a sequential circuits where, you know, you have your output, and it depends on inputs, just like the combinational or combinatorial circuit does. But in addition, the output depends on an output, because see here, the output is actually connected back to one of the inputs. This is actually called feedback. And feedback is not, you know, just for logic circuits. You'll see feedback in analog circuits, okay, in your other classes. In fact, well, I know the EEs take a control class. I think the CPEs eventually do at some point, but I think the EEs take it earlier in the curriculum. But when you take a controls class, that's like day one. Day one of control is feedback. And, you know, you go into the whole theory of feedback, and you know that's like just about like a quarter-long class. So it's a pretty complicated topic. But for right now, that's really the difference between a sequential circuit that has memory and a combinatorial circuit that doesn't have memory. The sequential circuit has feedback, that its output not only depends on inputs, but also on outputs. All right, well, why is memory important? Well, you may already think, okay, memory, you know, it does storage, and I'm sure you can think of, you know, reasons why that would be important. But one thing you may not think about that is important, and we wouldn't be able to do without memory, is that if you have a sequence of events, you know, just being very general here, you know, say you have some event that you label A, and from A, you go to event B, and then from event B, you go to another event C, and so on. Okay, you're going in some sort of sequence of events. Well, in order to do any sort of sequence, in order to know what the next step is, you have to remember where you were. Right? In order to progress through a series of sequence, you need memory to remember where you were at. You know, otherwise you wouldn't know, you know, which event is next. Okay, and you're gonna see that next week when we get to something called a finite state machine. Okay, FSM is the acronym for finite state machine. You will see that these finite state machines will perform some sequence of events. And at that time, you'll learn about something called a state diagram, which could also be called an event diagram. You know, it's a pictorial, similar to what I just wrote on the board here, of showing a sequence of events. And the digital logic circuitry that can perform that sequence is this FSM. And you'll see that FSM has memory. Okay, otherwise it wouldn't know, you know, where it was at, and therefore it wouldn't know what's next. Okay. All right, so some, you know, kind of basic overview, you know, discussion on sequential circuitry here. Now we're going to get more specific. Okay, now we're going to look at the actual circuitry that has memory, okay, that can store data. And that circuitry, it's called a latch. And here's an example of a latch. Okay, this is a NAND latch. Obviously, it's called a NAND latch because it's made out of NAND gates. But you can also make a latch out of NOR gates. In fact, that's what the activity is going to be. Or one of the activities, actually two activities. One activity is, you know, after I go through how the NAND latch works, I want you to take the approach that I show you and apply it to a NOR latch. So, just like two's complement has two meanings based on whether you're looking at two's complement as a noun or as a verb, right? Remember we talked about that last week. The noun was that listing I gave you of the numbers, like the 4-bit two's complement numbers. And then when you take the two's complement, right, the verb, the action, you're negating whatever binary number you're starting with. Well, latch also has two meanings depending on whether it's a noun or a verb. As a noun, it means this circuit. Okay, this circuit, as we're going to see, can store a bit, can store a single bit. And then latch as a verb means to store. Right? If I say, we're latching this data, it just means we're storing that data. Right? The data being, zeros and ones. At this point, it should make sense to you that data corresponds with zeros and ones, right? Because we've shown how zeros and ones, even in of themselves, they're just voltage levels. Zeros and ones can represent anything we want them to based on the circuitry that we design around those zeros and ones, right? Because we've seen how zeros and ones can represent binary numbers, whether that be unsigned or signed, two's complement. Also, we have seen that zeros and ones can represent hex characters, right? You did that in lab 3, right? The zeros and ones going into the decoder, and based on your design of that decoder, well, you made it display hex characters. Okay. All right, so this is the actual circuit of the NAND latch. And the particular feature of this latch is notice that, well, actually, before I tell you this, I should also write here that S and R, these are inputs. Okay, in Q and not Q, these are outputs. So it's two outputs, two inputs. And the peculiar feature of this is that this output Q connects down to one of the inputs of this NAND gate. And then this output not Q connects to one of the inputs of this output. That type of connection is called cross-coupled. Cross-coupled. Right, you kind of see where the name comes from, right? Because in the diagram, those connections are crossing. So that's what you'll always have with the latch. You always have this cross-coupling connection between the gates. So, a NOR latch would just be the same looking diagram. You would just have NOR gate symbols instead of NAND gates. That's the only difference. Okay. All right. So this is like the actual circuit. But what we're going to do next is we're going to look at what's called an analysis circuit, where this isn't what you would actually hook up, but this represents this circuit that you would actually hook up or actually model in system verify. And you see, the reason why this is an analysis circuit is because, see, it's got this block here, TD. TD stands for time delay. Not that we could actually hook up a time delay, right? And you see, there's a Q plus on the left side of this time delay, and there's a Q on the right side. This Q, that's the present state of the output. The present state of output Q. Right? And Q plus, that's the next state of output Q. Okay, so, Q is what it is at this time. Q plus is what it's going to be next. Okay, after this time. Okay. And you can see we got our two NAND gates. Here's the S input, here's the R input. And now we're gonna make a truth table. Okay, and on the input side of this truth table, we got S and R and also the present state of Q. And on the output side of the truth table is the next state of Q. So I've got three inputs here, right? S, R, and present state of Q. So if I have three inputs where each of those inputs is a bit, right? Can either be a 0 or 1. How many rows am I going to have? How many unique combinations can I have if there's 3 bits? 8, right? Because 2 to the 3, right? Remember, 2 to the number of bits equals the number of values, right? So all 3 could be 0. 0, 0, 1, 0, 1, 0, 0, 1, 1. You've done this a number of times now, right? I'm just counting in binary here. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. I think I got it, right? 2, 4, 6, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. Again, if I make an error, let me know. Okay. All right. So the next thing we're going to do now is we're going to fill in what the next state of Q is by analyzing this circuit, and that's where having your truth table for an AND gate comes in handy, right? Because that's how we're going to determine the output of AND gates, by looking at this truth table. Now, like we've done before, we can gain some insight into this truth table by dividing it in half. All right, remember we did this before when we were talking about universal gates, and we were saying, well, if you look at the bottom 2 rows of the truth table, if you make one input to an AND gate of 1, well, then the output's just going to be the opposite of the other input. For instance, you have an inverter between the output and that other input, the one that's not connected to one. Then we also said, well, if you connect the inputs together, you're either in the top row or the bottom row, because if you tie inputs together, it can't have a different voltage, right? So it can't be a different value. So again, that was another way to make an inverter out of an AND gate, right? Because up here, 0's in, you get a 1 out. Down here, 1's in, you get a 0. Right? So you remember that? Okay, well, here for this particular analysis, what's handy is looking at the top 2 rows. Right? Because if you look at the top 2 rows, what it tells us is if one input to an AND gate is a 0, I don't have to know what the other input is, because the output's going to be 1 regardless. Okay? See, that can help us fill out this truth table, because now when I do this first row, S is 0 and R is 0. Well, right away, because I have insight into the table by looking at these top 2 rows, I know right away that the output of this man is going to be a 1 and the output of that man is going to be a 1. See, I don't even have to think about what this other input is equal to, because if you have one input to an AND gate is 0, you're going to get a 1 out regardless what the other input is. So is that clear to everybody? That kind of key to what we're going to be doing. Okay, so if in this top row here, when we have all 0s, right, our next state Q is just going to be 1 because S is 0. Right, and in fact, that's going to be true for the next row also. Because S is 0. Okay. So any questions on these first 2 rows before we go to the next 2? All right. So now we look at these next 2 rows. We got S 0 and R is 1 and Q is 0. Okay, but look again. If I have a 0 going into this NAND gate here, where the output of that NAND gate's the next state of Q, well, it's going to be a 1, right? Because again, you get 1 0 going into an NAND, the output's going to be 1. So this is going to be a 1 for this third. Oops, guys, I got skewed for this here. So this is a 1. This is a 1. And then also this fourth row, X is still 0, so next data queue is still going to be a 1 here, right? Right, so is every, oops, sorry, it's getting skewed. Right, so there we go. I think that's lined up better. So for these first 4 rows, our next data queue is just going to equal 1. Everybody agree?
So what gets applied on the NAND gate over there? Is it Q or Q plus on the R NAND gate?
This is Q plus right here. The output of this.
You know what I'm saying on the R NAND gate on the R.
Oh, right here.
Yeah, what is applied with the R? Is it Q plus? Like,
Oh, this input is. Yeah, this input's connected to Q. Yeah, so whatever we put here would also be. Yeah. Yeah, but you see, since we're after this, when this is a 0, I don't even care what that is, right? Because whatever that's outputting is not going to matter, right? Because as long as I got 1 0 at the input of this NAND, this is going to be 1 regardless what this is. Okay, so yeah, but yeah, you'll see that will be important coming up. Okay, so is everybody okay up to this point here? Everybody see where I'm getting this? All right, so now, okay, this 5th row here. S is a 1, R is a 0, and Q is 0. So this is where what you brought up is important, right? Because now when I look at the output of this NAND gate next data Q, where this is a 1, you know, this other input does matter now, right? To determine what that output is. So since present state of Q is 0 and it's connected directly to this other input of this NAND gate, I've got 2 zeros at the input here, which means I'm going to get a 1.
well, we don't care if we don't care if R is 0, right? Because R is 0 is automatically 1.
That's true. That's true. Yeah, I could have just left it like that. We'd still get a 1. That's right. But the key thing is, you know, where this is a 1, I had to know what this was. Okay, but now we know that this is a 1. So now I've got 2 1s coming into this NAND gate. And 2 1s will give me a 0. All right, so for this 5th row, next data Q is going to be a 0. Everybody agree with that? All right, so now the next row, we still have S equal to 1, we still have R equal to 0, but now present state of Q is 1. Okay, but as what we said earlier, this is still a 0, so we'll still have a 1 out of here. And again, we get 2 1s into this NAND gate, so we get a 0 out. So this would be a 0. Okay, everybody agree with that? All right, now let's do the next row. Okay, the next row, we got S equal to 1, R equal to 1, and present data Q equals 0, right? That's this 7 right here. So let's see, this is a 1, so I have to know what the other input is. It's connected to this present state of Q, so that's a 0. So 1 and a 0 gives me a 1 out. And now 2 1s into this NAND gate gives me a 0 out. So this would be a 0. Okay. And let's do the last one. Let's see, last one, R1, present state of Q. Right, this 1 is connected right to this input. So 2 1s, that's going to give us a 0. And any 1 0 at the input will make this a 1. Okay, so did I make any mistakes? Everybody agree? All right, the next thing we're going to do is we're going to take this truth table that's got the 8 rows, and we're going to partition it like this. We're going to partition it every 2 rows, and you'll see why in just a moment. Okay, so I'm going to partition these 2 rows. I'm going to partition those 2 rows. partition these two rows. And now I'm just going to make a slightly more compact truth table where I'm just going to have S and R along with the next data Q. So if we look, let's see which one. We're going to start with these two rows here. Okay, you'll see why I'm skipping this top two rows in just a second. So here for these two rows, S is 0 and R is 1. And if you just look at the next data Q, when S is 0 and R is 1, right? These two rows, look, the next data Q is 1. All right. And then we can just look at these two rows where S is 1 and R is 0, and you can see that the next state of Q is going to be 0. Now, when we have this condition here, when the next state of Q is going to equal 1, when S is 0 and R is 1, we call this the set condition. And what set means here is that the next state of Q is 1. It just so happens that for a NAND latch, in order for the next state of Q to equal 1, S has to be 0 and R has to be 1. But if you have a different latch, let's say you have a NOR latch, well, you're going to see that the next state of Q for a NOR latch equaling 1 has a different value of inputs. So what's important to understand is the value of the inputs is not what set means. It's the value of the next state of Q. Because the next state of Q is going to be 1 when S is 0 and R is 1, that's why we say that the NAND latch is set. You're going to see the NOR latch is set for a different combination of S and R. Okay, that's the biggest confusion point usually with something like this. You know, students will look at what the inputs equal and think that's what's meant by set, but it's not that. It's what the output equals that makes it set. Okay. All right. And then this third row, when the next state of Q is 0, that's called reset. And it's the same reasoning. Reset means next state of Q is 0. Again, it doesn't have anything to do with what the input. It just so happens these are the inputs you need for a NAND latch to get the next state equals 0. Okay, so everybody good up to this point? All right, the next two rows, these bottom two rows, is why this is called the latch and why this circuit can store data. Okay, because look, for this NAND latch, if both S and R are 1, look, next state of Q, well, if present state of Q is 0, the next state of Q is going to be 0. If the present state of Q is 1, the next state of Q is going to be 1. See, this is storage of data. If you maintain the same output value after a given amount of time, you've stored data, right? You maintain previous zeros and ones. So, you know, if these zeros and ones were part of a binary number, you have stored a binary number. Okay? So the shorthand way of writing what this long way truth table tells us is that when both inputs to a NAND latch are 1, next state of Q equals present state of Q. Right? Even though time has progressed, we still have the same data at the output. That's what storage of data is. Okay? See, this is why this circuit exists. See, this, you know, previous circuits we did, like these combinatorial type circuits we did prior to today, they can't do this. They can't retain previous data from a previous time. They don't have the ability because they don't have that feedback. They don't have memory. Okay?
Hello, theory, stuff.
Okay, that's still not memory though.
But like if you apply it to the same, like, then if you apply it to the same 400.
Oh, I see what you're saying. Yeah, it's an output going to an input, but it's an output going, it's an output of one module going to an input of another module. See, to have memory, you gotta have the output of a module going to an input of that same module.
Oh,
See,
okay.
that's a very good point, though. I can see your question, but yeah, in that case with the RCA, the reason why it's not memory is because it's the output of one module going to an input of a different module, not the same module. So yeah, that's a great question. Any other questions before we do the top row?
Then it is, they have to set the value for it to like start working, or.
Oh, I see what you're saying. Well, remember, these outputs, they're gonna have some value. Like when you first turn it on, power it up. It's either gonna be a 0 or a 1. So yeah, it's gonna start with some value. Now, we don't care what value it starts with in most cases. If you do care, at least in Verilog, you can initialize it to a particular value. It's a little trickier in like an actual like breadboarded circuit, although usually, I don't know if I can say this 100%, but usually like in a breadboarded circuit, when you first turn something on, usually the value would be 0 until you apply, voltage to it. But I think there are exceptions to that depending on the type of logic circuitry, because you're going to learn later on when you take electronic classes that there are different, like electronic circuitry that can give you the same gate. We call it, or they call them like families of ICs. There's, just to throw out some acronyms again, this isn't going to mean much, but when you take the class, you'll learn about, there's TTL circuitry, which stands for transistor logic, and there's CMOS circuitry, complementary metal oxide semiconductor. It's different electronic circuitry that gives you the same truth table, but it has different electronic features. That's where you get into, sometimes a 1 is 5 volts, sometimes a 1 is 3.3 volts, and it goes to that. So, yeah. Okay, well, the reason I saved the top row for last is because we can't get everything from this this table that we went through. Now, what we can get is that from these top 2 rows here, S and R are both 0. And you can see that next data Q is 1. All right, so that's what we can get. But the additional piece of information for this top row, we have to look at this actual circuit that you would connect. Again, remember, this is the analysis circuit because we put in this time delay. But this is what you would actually model in System Verilog or connect up on a breadboard if you were going to make this latch on a breadboard. And if you look at this actual circuit, when both S and R are 0, what's the output of those NAND gates going to be? Yeah, they're both going to be 1, right? Because again, if you have 1, 0 going into an AND gate, you don't have to know what the other input is, right? The output's going to be 1. So do you see a problem, based on what we know about Boolean algebra? If we get both outputs of this latch equal to a 1? Because in Boolean algebra, what does the bar over a variable mean? It means not that variable, right? Which means opposite the variable, right? Not Q means opposite Q. Well, this circuit, when both inputs are 0, it gives us both outputs equaling 1, and that doesn't make sense based on Boolean algebra, right? It doesn't make sense that not Q would be the same as Q based on what we know about Boolean algebra. So because this combination, both inputs being 0, gives us something that doesn't make sense really based on our base 2 algebra, right? Boolean algebra. We call this the forbidden state. Oops. Forbidden. Sometimes it's called ambiguous. Okay, so either word, forbidden, ambiguous. Meaning, since both inputs being 0 gives us outputs that don't make sense, according to Boolean algebra, we just want to avoid. You just want to avoid both inputs being 0. The way you avoid it is just never let both inputs equal 0 at the same time. So you see, the reason why this latch exists is because it gives us memory. This forbidden state is just baggage, just because it comes along with the storage. And a latch by itself is like the most primitive of storage elements. This was like the first circuit way back, and I think it was invented even before logic circuitry. It was quite a while ago. But this was sort of like the first circuit to exhibit, memory. Well, later on in the evolution, if you will, of storage elements, came the flip-flop. And the flip-flop is an improvement over the latch. You're going to see it still contains a latch, but it has additional circuitry that takes away some of the drawbacks of a latch. One drawback being that it has an ambiguous state in its truth table. There's actually another drawback of the latch that we'll get to coming up. Okay, but before I start talking about a flip-flop, I want to make sure there's no questions up to this point. And everybody following, everybody see why this is, we have to write this. This is called the storage state. Okay, because that's when storage of data is happening. Also, it's called the hold state. It's holding on to the data, right? It's storing it. I suppose you could call it the latch state too, but latch refers to the circuitry, so I think that's why they don't use latch for that. Although latch, the verb would fit in, I guess. But I've never heard anyone use latch for this. It's always either storage or hold. Okay, but any questions up to this point? We're going to have to take a break at some point here. Do you want to take a break now, or do you want me to keep going for a while longer and then take a break? It's probably going to be like 90 minutes. So this would be sort of like the halfway point. So why don't we take a break for 5 minutes and then we'll pick up with the flip-flop. Okay? So I'll start up again at like 9:50. You have a question?
Yeah. We'll go real quick off that math.
So this here, when we're doing this?
Okay, how to run it through. I think, yeah.
I mean, was it a particular row or you mean the whole thing?
Or like the analysis.
Well, all we're doing. See, we started out with these 8 rows of the truth table, right? And then to find what the output next data Q is, I'm just taking, I'm going row by row. So I started with this row, so S is 0, R is 0, Q is 0. And then this is where, again, if you look at the truth table of an AND gate, if one input to an AND gate is a 0, it doesn't matter what the other input is. See, the other input could be 0, 1. I'm still getting a 1 out. So when I analyze this, when I see that there's a 0 at the input of an AND, right away I can say the output's a 1. Right? Because I don't have to know what that is, because if this is a 0, if this is a 1, I'm still going to get a 1 out. So you see, that's how I got a 1.
Well, you have a 1.
Say that again?
What about if you have a 1?
For S?
Yeah.
All right, so let's see which, like say we do this row. There'd be a 1 here, a 0 here, a 0 here.
Yeah.
Well, if you have a 1, then you have to know what this other input is, right? Yeah. And this other input's connected to the output of this NAND gate. So I look at this NAND gate and I go, oh, I got a 0, so this has to be a 1. And then 2 1s give us a 0.
Okay.
So yeah, it's just putting the 1s and 0s for R, S, and Q, and then just looking at the NAND gate to get what the outputs are.
Okay.
And then specifically, we just want this next data.
And the last one's only 1 because the Q is determined.
This last row, the last row, these are all 1. So again, I have to know what this input is, right? So now I look at this output, and because this is one, I have to know what this input is, and this is connected right to the present state of Q, so this would be 2, 1. So I get a 0 out, and then a 0 and a 1 gives me a 1 out, right? Yeah.
Okay. Great.
Okay,
Thank you.
sure. Yeah, for the activity or one part of the activity, you're gonna have NOR gates instead of AND gates. So you're gonna have to do the same thing for a NOR gate, but it's the same approach. It's just now you gotta look at the truth table of the NOR gate. You're gonna see something similar. You're gonna see that, hey, if this input's equal to this, I don't have to know what the other input is because the output's always gonna be this.
Yeah, I feel that, like, I can really tell where to start and so. I think that was the part I was.
Oh, okay.
But I guess if you just.
Yeah, it's maybe it's this that, this is connected right to here. So whatever this is, it's the same here. Yeah, have you had circuits yet? Okay, yeah, circuits helps in this regard because when you have any sort of connection, it makes the voltage the same. And that's what these zeros and ones are. They're just voltages. So if I have two things connected, they have to have the same value. Yeah, it makes more sense when you take circuits. Yeah, it's not necessary to have circuits for this class, because all you gotta remember is, if you got an output connected right to an input, it's just the same 0 or 1, but it helps, I think, if someone has had it. But I mean, when you take circuits, knowing what you know now, you'd be ahead of the game, right?
Oh, for the midterm, like, what, like, I mean, you gave us that sheet already, like, so we know what.
Yeah, the topics, and then I would just go through like the different activities we've done, and I would go through what I talked about in class. I mean, I have recordings, so I mean, if you missed anything, I would, watch that, but.
Is it just like general, like, basic understanding of the concept you can, would that be enough?
Yeah, that's, well, I can't make any guarantees about what's, enough or anything like that, but all I can say is that I would think if someone's been understanding, that's the key thing, understanding, because sometimes people can rotely do something, but they don't really understand what they're doing, especially when I give them the answers. So I would just make sure when you go back and you review that you're actually understanding, not just trying to memorize, because, of course, like I said, what's on the midterm is likely to, be similar but different. That's the best way I can describe it, right? It's not going to be something you've seen before, but it should be something that, based on what you've seen before, you can do it. That's like any test, right? Except for memorization tests.
I suck at memorization. I want to practice that.
Okay, so I think it's time to pick up here again. So like I said, the latch was sort of like the first logic circuitry, if you will, that could store data, but it has some drawbacks. Okay, one drawback is, again, it's got this forbidden state, right? Which, I mean, it's not that big of a deal because it's easily avoidable, but still, it's something you got to kind of think about. And then also another drawback of a latch is that it's sensitive to noise. Okay, and I'll talk more about what I mean by that coming up, but those are really the two drawbacks of a latch. What's that? The first drawback is that it has the state that's forbidden. Yeah, which again, it's easily avoidable, right? Because you just don't make the inputs, equal to what gives you that state. But again, if you didn't have it, it'd be nicer, right? You wouldn't have to think about it. So the next evolution, if you will, in storage element was the flip-flop. And the flip-flop, it's an edge sensitive latch. Okay, so this word edge sensitive, we're gonna talk about what that means. Now, on the table, I put a handout, and there should be enough for everyone at the table. I tried to put 4 at each table. Okay, it's this handout here. So if you take a look at this handout in the top left, that's the circuitry of what's called a D flip-flop. See right here? And can you see it contains a latch? See the latch right there, the cross-coupled NAND? So a D flip-flop, it's a latch with additional circuitry. See, there's a couple other NAND gates and there's an inverter. So, you know, you put these additional gates on the input side of a latch and you get this thing called a flip-flop. Now, on Canvas, okay, under this meeting 11, I put a YouTube video. And it's a really good YouTube video. It steps through and it shows you why that logic circuitry gives you the truth table that I'm about to give you. And it explains, you know, what edge sensitivity is, and I'm going to explain that also. But that video does a much better job than I could ever attempt to do in class because it uses animation, which I think is really necessary to really understand how that circuitry gives you this thing called edge sensitivity. Okay, so I encourage you to watch that video. It's like a 15 or 20-minute video. It's not that long, but it's well done. All right, but I'm going to give you the straight and narrow, so to speak. Okay, not all the details that the video gives you. So first of all, the D flip-flop, it comes in two flavors. Okay, and I drawn the symbol for each of them. And can you see the difference between the two symbols? It's a very subtle difference. But do you see the difference?
One's got an inverter.
Yeah, right here on the CLK input, which is short for clock. Okay, these are the inputs. Okay, there's a D input and there's a clock input. This triangle that you see on the symbol by the clock input, that means edge sensitivity. Okay, that's just a symbolic way of representing something that's edge sensitive. And again, we're going to talk about what edge sensitive means coming up. And then again, the outputs are the Q and the not Q. Okay, so yeah, the only difference between the two is on the clock input, this one has this little bubble and this one doesn't. Okay, and I'll talk about what that symbolizes here coming up. But let's look at the truth tables for this D flip-flop. And we've got three inputs here in the truth table. We have the D input, we got the present state of Q again, and then the clock. And then the output is the next state of Q. So we can have 4 combinations of D and Q. You're going to see that the clock input, because this is what we call edge sensitive, for this type of D flip-flop, the clock input is represented with an arrow going up. And I'm going to talk about what the arrow going up means in just a second. Okay. For this other type of flip-flop, D flip-flop, okay, we'd have 4 values or 4 combinations for D and present state of Q. And then here, the clock would have an arrow going down. Okay, now I'm going to fill out the rest of the truth table, and then I'm going to explain it, you know, and also explain those arrows. But the rest of the truth table would be this. When the D input is a 0, the next state of Q is going to be 0. When the D input's a 1, the next state of Q is going to be 1. And the same thing over here. Okay, so what does this all mean? Well, first of all, where can I write this? Let's erase some of this over here. We can erase. All right, so I'm coming over here. Okay, what the upward arrow means, it's referring to the time that the signal, the square wave on the clock input, goes from a 0 to a 1. Okay, so that arrow is a way to symbolize the time that the square wave on the clock input goes from a 0 to a 1. See, we call that a rising edge. Okay, that 0 to 1 transition, we call it a rising edge. Okay, sometimes it's called a leading edge, and sometimes it's called positive edge. Maybe I should write those down too. These all mean the same thing. Unfortunately, there's more than one word to describe this. Okay, so sometimes it's called the rising edge, sometimes it's called the leading edge, and sometimes it's called the positive edge. All three mean the same thing. Well, you can probably guess then what the downward arrow means. It's symbolizing a 1 to 0 transition. So the time at which the square wave on the clock input changes from a 1 to 0. Okay, that's called falling edge. Trailing edge. And negative edge. Okay, so you see that's what the little bubble indicates. See, the little bubble indicates that this is falling edge, right? The arrow going down, and no bubble means it's rising edge, arrow going up. So the way you read this truth table is that if D is 0 and present state of Q is 0, at the time of the 0 to 1 transition of the clock, next state of Q will be 0. If you have D equal to 1, present state of Q equal to 1, at the time of the 0 to 1 transition of the clock, next state of Q is going to be 0. Okay, third row, if the D input is 1, present state of Q is 0, at the time of the 0 to 1 transition of the clock, next state of Q will be 1. Okay, and same idea here, right? You have a 1 and a 1, at the time of the 0 to 1 transition of the clock, next state of Q will be 1. And here it's the same thing, except it's at the time of the 1 to 0 transition of the clock instead of the time of the 0 to 1 transition of the clock. That's the only difference between the two. And that's what's meant by edge sensitive. See, these flip-flops are sensitive to either the rising edge of the clock or the falling edge of the clock. That's what's meant by edge, is that transition either from 0 to 1 or from 1 to 0. Okay? So the way you can summarize both of these is that the next state of Q will equal whatever on input D at the time of the appropriate clock transition. And what I mean by appropriate is if you have this type of D flip-flop, the appropriate transition is the 0 to 1 transition. And if you have this type, the appropriate time is the 1 to 0 transition. Okay? So the key thing here is that the only time that the next state of Q is going to equal whatever is on input D is at the appropriate transition time. All other time, other than that appropriate transition of the clock, the output Q is just going to remain what it was. See, the only time that the Q output could possibly change with this type of device, this flip-flop, is at the time of the appropriate clock transition. That's what makes it edge sensitive. So you see, the two advantages that the flip-flop has over the latch is, look, first of all, in the truth table, in either one of these truth tables, there's no ambiguous state. So you see, it has no ambiguous or forbidden state in the truth table. Ambiguous. In truth table. Now you're going to see when we get to a timing diagram that has a flip-flop, you're going to see that you can still have an ambiguous situation when it's a flip-flop, but it's not in the truth table. Okay, so it's still an advantage over a latch. And the second advantage is that flip-flops are less sensitive to noise. Okay, now, again, where you haven't, or at least the CPs, or maybe mostly the CPs, or most of the CPs, I don't think, well, how many CPEs are there? I think it's about half the class, right? Half the class. How many CPs have taken any sort of like EE lab where you've had equipment like voltmeters or oscilloscopes, or so just a few people? Okay, not many of the CPs, but the EEs have, right? Because in the 151 lab, right? So yeah, until you take a lab, I don't know if there's much appreciation for this, but you know, once you take an EE lab, one of the first things you learn is that you know, circuits have noise, okay, which is just caused by extraneous, you know, electromagnetic energy that's, you know, in our environment, right? I mean, there's cell phone communications going on, and you know, there's equipment that, you know, even though it's shielded, there's still electromagnetic energy that leaks from computers and phones and, you know, power lines and what have you. So, you know, when you look at a signal like on an oscilloscope, you'll see fuzziness, and that fuzziness is noise. It's rapid variations in voltage, and engineers are always trying to reduce noise. Yeah, you can, you know, have a career just, you know, different ways trying to eliminate noise. Okay? And also the opposite, like when you're encrypting, or, you know, you intentionally put signals into noise so your adversaries can't, you know, see your communications and stuff like that. But how it pertains to this is that noise, the way you can think of noise is that it's voltage spikes. It's like quick changes in voltage. So a latch, which depends on levels, because again, these zeros and ones are voltages, right? So when you have 0 volts or 0, that's like ideally 0 volts. When you have a 1, that's ideally some amount of voltage. Well, these voltages, they're not necessarily always steady. And especially if you're in a noisy environment, the voltages will fluctuate. So it's possible that you could have a 0 change to a 1, or a 1 change to a 0 because of noise. And if that happens, you're going to get an unintended output, right? So noise can change what you're expecting to see at an output. Well, latches, because they depend on voltage levels, right? They're not edge sensitive. They're more susceptible to noise, because a flip-flop, because it's edge sensitive, where the output can only change at that instant in time when the clock changes, either from a 0 to a 1 or a 1 to a 0. Well, your noise spike would have to happen right at that time for there to be an effect. If you have a flip-flop and the noise happens at any other time other than the appropriate transition of the clock, it's not going to affect anything, or most likely it won't. Okay. Now, it's not immune from noise, because yeah, you could get a voltage spike right at that time of that transition of the clock, but it's less probable than for a latch, because a latch isn't edge sensitive at all. So wherever you get the noise could cause a problem, you know, whatever time you get it. Okay. So those are the two advantages of flip-flops over latches. They both store data, but the flip-flop doesn't have the ambiguous state in its truth table, and it's less susceptible to noise. Now, the other thing I want to mention before we move on here is that the D flip-flop is only one kind of flip-flop. Okay, there are other types of flip-flops. There's a flip-flop called the JK flip-flop. You'll probably learn about that in a later class. Okay, we don't cover that in this class. You know, the JK is a little bit more sophisticated than a D flip-flop is. It has like a additional feature called toggle, which sometimes is handy. But if you understand a D flip-flop, any other flip-flop you come across, without much more effort, I think you can understand that. Okay. All right. So, any questions up to this point? Okay, because now it's time to turn the camera. And also now things are going to get a little bit more muddled, unfortunately. Okay, because, you know, this is your like basic run-of-the-mill D flip-flop, right? It has a D input, has a clock input. Again, a clock signal is just some square wave signal. And often, not always, but often the square wave that you put on the clock input of a flip-flop, often it's what we call periodic. Okay, so it's low for a certain amount of time, then it's high for that same certain amount of time, then it's low for that same certain amount of time, and it's high for that certain amount of time, you know, it's periodic. But you can connect any square wave to a clock input. It doesn't have to be periodic. Like I could, you know, have a very short pulse and then wait a long time and then have a long period where it's one. All right, so it doesn't have to be periodic, but a lot of times it is. And technically that's what the term clock in digital circuits means. It means a periodic square wave. Okay. Okay, well, but really useful flip-flops have additional inputs. Often, and all of these are inputs. Often, in addition to clock and the D input, because you always have these inputs, but often you'll have additional inputs to a flip-flop. You'll have an input called enable. You'll have an input called reset. Now, reset is the same thing. I have it written over on the left side there. Reset is the same thing as clear. Also, enable is the same thing as enter or load. So these are all words that mean the same thing here. And then set, I don't think there's another word for set. I can't think of one. Okay, but you'll have these additional inputs. Also, inputs can either be active low or active high. Inputs can either be synchronous or asynchronous. And also, you can have rising edge trigger or falling edge trigger. So rising edge trigger refers to what we talked about here. Okay, where the sensitivity is to the 0-1 transition of the clock. Okay, that's the rising edge. And if you have a device that's sensitive to that edge, we say the device is rising edge trigger. Okay, and then falling edge trigger, you know, refers to the 1 to 0 transition. Okay, so we already talked about rising edge and falling edge. Okay. All right. Well, first, enable. Enable is an input. Let's see. Enable. When enabled, Q, next data Q can equal B. So this is sort of like an addition to what we were talking about here, that in order to get either one of these truth tables, if you have an enable input, that enable input has to be activated in order for you to get these truth tables. If the enable is not activated, then the flip-flop is just going to remain in whatever state it was in. Okay, so that's the enable. Reset. Okay, when activated. Actually, instead of saying enable, when enabled, which is repetitive, I should say when activated. Activated. And I'll talk about how you activate it coming up. Okay, reset when activated. Next data Q is going to equal 0. Regardless the other inputs. Regardless. Or let's just say regardless what D is equal to. Regardless D's value. Okay, so when reset is activated, your Q output is going to be 0 no matter what your Q input is doing. Okay, and then set. Okay, when activated, the next data Q is going to equal 1. That's a 1. Regardless D's value. Okay, so both reset and set, they're sort of like dominant inputs that when they're activated, they take over. And then enable, as the word implies, well, the flip-flop's really not going to do anything until you enable. Okay. All right, so that's what these three inputs mean. Now, each one of these inputs can either be active low or active high. And what that means, or what active low means, is that a 0 activates that input. Or activates input, I should say. So if you have an active low reset, you have to make the reset input equal to a 0 to get the flip-flop to reset, to get the outputs to go to 0. Okay, if it's an active low set, that set input has to be a 0 in order to get the Q to go to 1. Okay, and then if it's active high, as you might guess, it takes a 1 to activate that input. Right, so an active high enable, the enable would have to be a 1 in order for the flip-flop to do anything. Okay, in order for the flip-flop to follow whatever truth table we have for that flip-flop. Okay, so there could be active low reset, active high reset, active low enable, active high enable. All these three inputs can either be active low or active high.
You're saying these inputs that these are clock inputs?
No, these are additional inputs to what we already have. So a D flip-flop will always have a D input and always have a clock input, but sometimes it will also have a reset. Well, actually, resets are usually shown on the bottom in a set.
So are they like set values to like D? Are they like set values to the inputs?
Well, no, this D input can be 0 or 1. S and R, again, all these inputs are binary, they're bits, so they can be either 0 or 1. It's just that if you have an active low, it means you got to have a 0 to make that input happen. Like if you have a reset input and it's active low, it takes a 0 here to get it to reset. Okay, if it's not resetting and it's not setting, and if you don't have an enable, well, then it's just going to work like this truth table. But if you have an additional enable, like sometimes you'll have another input enable. And when you have an enable, if you're not setting, if you're not resetting, and enable's activated, well, then you'll get this truth table. Okay. So any other questions up to this point? Because there's one more. This is the one that usually gives most people trouble, or can give some people trouble. And that's synchronous and asynchronous. Okay, what synchronous means is that input depends on appropriate edge of clock. Appropriate clock edge. And what asynchronous means is input does not depend on clock. So if it's, let's say you have an asynchronous active low reset. Well, if it's asynchronous, the minute that active low reset goes to 0, the reset's going to happen and the Q output's going to go to 0. If it's a synchronous active low reset, it's not enough just for the reset to go to 0. In addition, the reset has to be a 0 at the time the clock transition happens. So if it's a rising edge, you'd also have to have the 0 to 1 transition of the clock to occur while that active low reset is 0 in order for the reset to happen. Okay, so the key difference between the two is one depends on the clock, the other one doesn't. Okay, asynchronous does not depend on the clock, synchronous does. Now we're gonna do a timing diagram, and I think when you see the timing diagram, this starts to make more sense. It's kind of hard to, I think for most people, it's kind of hard to understand it just with words. I think when we do a timing diagram, you actually see like a picture of it. It should make more sense, hopefully. Okay. just a few more things here. You know, I already mentioned that, you know, these inputs are shown on the symbol like I've shown here. Now, if there's not a little bubble, like see, I didn't put a little bubble on these inputs, that means it's active high. So you see, this would be a way of showing an active high set, an active high reset, and an active high enable. If they were active low, there would be a little bubble. Yes, that's set, sorry. Yeah, so like your active low reset would have a bubble, your active low set would have a bubble. And if you had an active low enable, it would have a little bubble. So anytime you see a little bubble on an input, that means active low. Now for a clock, like we said earlier, this means falling edge, right? And rising edge. Okay, but for inputs, if you see a bubble active low, if you don't see a bubble active high, D is never active low or active high. D is, well, D stands for data. That's just, you know, 0 or 1, depending on what the data at that input is, you know, whatever the bit value is. Okay, the other thing, and this confuses people, but, you know, don't shoot the messenger. I didn't make this up. It's just the way it is. And that's in timing diagrams, as well as on these block diagrams of the flip-flops, a bar means active low. It doesn't mean not. Like this doesn't mean not S and not Q. Now this does mean, or not R. This does mean not Q. All right, but this doesn't mean not R. It just means active low reset. And this means active low set. And there should be a bar over here. And active low enable. And I know it's confusing, but like I said, don't shoot the messenger. That's just the way it is. Okay, so any questions up to this point? Now we're going to take what we talked about here and apply it to a timing diagram. So hopefully that will reinforce what we've talked about. But any questions up to this point?
Is the bar over the S how it be confusing? Is that the same system Verilog?
Oh, in system Verilog, no. In system Verilog, anytime you put like a not, whether it's the tilde if it's an equation, or the exclamation if it's like in a sensitivity list of like an if statement or something, that's always not. Active low and active high. Well, actually, active low and active high in system Verilog, yeah, it's basically done the same way, but you don't do like a bitwise active low or active high because you don't write like equations. So the active low, active high in system Verilog would just be for like in an if statement, and it would still be like an exclamation point. Now, you're going to see, you know, by the end of lecture today, that there's a particular way of making it either falling edge or rising edge. Because you can do both in the code, and I'll explain both. And also, there's a particular way of doing synchronous and asynchronous in the code, which again, I'll go over. But as far as active low, active high, like in an if statement or like in a case statement, it's still the exclamation point. And like I said, you would never do like active low or active high in an equation, so it doesn't really apply there. Okay, so any other questions up to this point? All right, so let's do a timing diagram, and this is the other part of the activity. Hey, one part of the activity today is you know, taking a NOR latch and basically doing the analysis I did for the NAND latch, and you know, except you're doing it for the NOR latch. The other part of the activity is looking at these flip-flops that have like reset, set, and you know, active low, active high, and asynchronous, synchronous, and coming up with the timing diagram. So this is, you know, an example I want to go through. So you can see there's an active low reset. Again, this means active low. So this active low reset, it's high, then it goes low, then it goes high, then it goes low. Okay, what people do sometimes, and it's the reason why I'm emphasizing this, is, you know, and I can understand why people would make this error. You know, they look at the bar and they go, oh, not R, and they flip this. You know, they go, I got to flip this. But no, it's as written, it just means active low. Okay, and this is active low also for set. And then this is our D input, and then here's our clock input, and then we're gonna figure out what the Q is from these set of inputs. Now, this particular flip-flop doesn't have an enable, right? An enable's not shown. If an enable's not shown, it's understood that, there isn't an enable, so it doesn't apply, or the enable is just 1 all the time. Okay, it's active high and it's 1. This flip-flop will do something, right? Because it wouldn't make sense to do this timing diagram if the enable wasn't enabled, right? Because if the enable is not enabled, then flip-flop's basically not going to do anything, right? It just keeps what it currently has as its output. Okay. All right. So as other timing diagrams that you've seen and we've talked about, t equal to 0 is over here, and time progresses as we go left to right. So let's look at what we have at t equal to 0. Well, the active low reset is high, meaning it's not active. Okay. The active low set is also high. You can see it goes low over here. So it starts off high. So it means it's not active. So we're not resetting, we're not setting. The D input's a 1, and then the clock is 0. And then over here, we're told that this is a rising edge triggered D flip-flop. Right? So that means it's sensitive to what edge of the clock? Rising edge is which edge? 0 to 1 or 1 to 0? 0 to 1. So you see, it's the 0 to 1 edges that matter, since this is rising. Right. So I'm just identifying the rising edges of the clock. Okay. Okay. Also, our active low reset is synchronous, right? So that means it depends on the appropriate clock transition, which in this case is the rising edge. The active low set is asynchronous. So that means it doesn't depend on the clock. Okay, so any questions about this here? Because each one of your activity problems will have this information. It will tell you whether it's rising edge or falling edge. It will tell you active low, active high. It will tell you synchronous, asynchronous. So everyone understands those terms? All right, so now, the Q output, when we start at t to the 0, since this flip-flop hasn't been reset and it hasn't been set, right? Because those aren't activated, right? They're active low and they're both high at t to the 0. Well, at t to the 0, we don't know what the Q output is. I mean, the Q output is either a 0 or a 1, but based on the information we have, we don't know what it is at the start. So in a timing diagram, if you don't know what an output is, you can just put like an X or a question mark, whatever you want to put. Sometimes people put X's, sometimes they put question marks. Right? So at the start, we don't know what the Q output is. Now, if this reset had been asynchronous and it started at a 0 at t equals 0, then we would know the Q output is 0. Right? Because if I have an active low asynchronous reset, asynchronous means it doesn't depend on the clock. And if it's active right at t equal to 0, well, then I would know my Q would be 0 right at t equal to 0, right? But we don't have that situation, right? Because see, the reset doesn't go low until some time after t equal to 0. Okay, so let's look at this time right here. Okay, this time right here, this active low reset, that's synchronous, goes low. So what do you think is going to happen at that time, that active low synchronous reset goes low? Is reset going to happen since it's synchronous? Any guesses?
No.
It's not, right? Why?
There's a clock.
Right, again, because synchronous depends on the clock. You not only have to have that input, if it's a synchronous input, you not only have to have that input activated, but you also have to have it activated during the time of the appropriate transition of the clock, which is a 0 to 1 transition in this case, right? Because it's rising edge. So see, the reset won't actually happen until this time, right? The time that we get the 0 to 1 transition of the clock. So you see, we'll have a question mark. We won't know what the output is until right here, right? Because at the time of that 0 to 1 transition of the clock, the active low reset is 0, which will make the reset happen. Okay, so whatever it was before, just pretend that this question mark is like in the middle, because we don't know what it is. Well, it will go low, right? It will become a 0 at that time, right? Does everybody see what I did there? See, if this was asynchronous, then the reset wouldn't happen here, right? Because if it's asynchronous, it doesn't depend on the clock. So the minute an asynchronous input becomes active, it happens, right? So you see, that would be the difference between an asynchronous reset and a synchronous in this problem. If it's asynchronous, it would go low here. But since it's synchronous, you've got to have the 0 to 1 transition of the clock since it's rising edge. If you understand that, that's usually the biggest hangup with these timing diagrams. Some people have a hard time with asynchronous and synchronous, the difference, but that's the difference. So, is everybody good? Okay, so we just progress on now. So here, the active low reset goes high, so we're not resetting. Also, the active low set is high, so we're not setting. So if you're not resetting and you're not setting, then the output's going to depend on what the D value is at the time of the 0 to 1 transition of the clock. Okay, so if your reset's not activated and your set's not activated, now to get what the output is, just look at what D equals at the time of the rising edge of the clock. So our next rising edge of the clock is right here, and D is a 1. So Q will stay at 0 until the time of this rising edge, and then it goes to a 1. Okay. See, for all other time other than the edges of the clock, the appropriate edges of the clock, Q's just going to stay what it was. Okay. All right. So let's see. Here at this edge of this clock, again, we're not resetting, we're not setting. So our Q is just going to equal what D is. So Q is going to stay a 1 until it gets to this edge time, and then it goes to a 0, right? It equals D. All right. You see why it's called edge sensitive now? All right, let's see. All right, now, at this time here, okay, this edge of the clock, okay, we're not resetting because it's still high. We're not setting. And if we draw up a line, I mean, it's close. Okay, but you see this edge is right before this goes low. So right at this time here, the Q output will go back to high. Now, the reason I made this really close is because that was a memory jogger to me to mention and to ask you, what do you think would happen if D here was changing right at the same time as this rising edge of the clock? Like if D here was going 1 to 0 at the same time this clock was on its rising edge, what do you think would happen? So you have a change in D happening at the same time as that appropriate edge of the clock.
For the time error,
Close. I mean, it basically is a timing error because you would never want that to happen, right? Because if you have a change in D occurring at the same time as your appropriate edge of the clock, what Q equals, flip a coin. It could either be a 1 or 0. You don't know. So even though a flip-flop doesn't have an ambiguous state in the truth table, you can still cause an ambiguous situation. See, this would be ambiguous. If you got a change in D happening right at the same time as the edge of the clock, you don't know what you're going to get at the output. Again, you could flip a coin. Half the time it's going to be a 0, half the time it's going to be a 1. So you still have a concern, with latches, the concern is, you don't want both inputs being 0. With the edge sensitive flip-flop like this, the concern is you don't want D changing at the same time as your clock is changing. All right, does that make sense? Now, in the solutions for your activity, I think there's a couple of, at least one time of this in the solutions. And the person that made the solutions, I'm not sure if it was Dr. Benson or Dr. Mealy, but they would tell their students that when you have a situation like this, to take the value of D right before the transition. So you know, like if this was going from 1 to 0 at the same time as this clock edge here, they would tell their students just take the value of D before, so take it as a 1 in this case. I mean, you can do that, but in reality, that's not gonna what's gonna happen. Like I said, in reality, you don't know what it's gonna. You can't count on it being 1 or 0. Okay, so you know, for the purposes of the activity, do whatever you want. You can just say ambiguous, or you can put, you know, the value before. I don't care. What I do care about is that when you go to 233, that you know in that class that you don't want this because in your microprocessor, if you have a situation like this, your microprocessor is going to have a glitch and it's not going to work the way you want it to work, or at least it won't work all the time. It may work every once in a while, because every once in a while it might be the value you want, but it won't be reliable. Okay, so let's keep going here. So, okay, when we get to the next edge of the clock here, we're not resetting, we're not setting. So let's see, D is 0, so D would go to 0 here. Okay, so now, actually, let's back up here. Okay, because something happens now. After this rising edge of the clock, look what happens to set. The active low set, which is asynchronous, goes low. So what's going to happen right here since it's asynchronous? Right, output's going to go to 1 because the set's going to happen, because if it's asynchronous, it doesn't depend on the clock. So you see, the Q output would be a 0 until that set happens, then it would go high. Okay, and it would stay high until this next clock edge, right? Because at this next clock edge, we're not setting, we're not resetting. So D is 0, so this would go to 0. Yeah, let's see, is there anything else? Oh, and then, yeah, what's going to happen? What's the last thing that's going to happen? Yes, that's going to happen again right here. So go back to 1. Okay? Any questions? If you understand this example, you should be able to do the activity that has the timing diagrams. It's just practice with this. Again, if you have any questions about this when you're going through the activity, especially asynchronous and synchronous, because again, for CPE133, it's very important that you have a good understanding of what that is. Because in that microprocessor, you have some inputs that are synchronous, most of them are synchronous, but you also have some asynchronous. Okay, all right, we're getting there. I told you it was going to be a long lecture today. But the next thing is, okay, how do you model this in System Verilog? Okay, how do you model a flip-flop? So first thing, you know, you got to give it a module name, like any module. So maybe you call it DFF. And then you're going to list or declare your inputs and outputs. Now for lab 5, your flip-flop is going to have an enable. It's going to have a reset. It's going to have a set. Flip-flops always have a D input, and they always have a clock input. So you're going to have, what, like 5 inputs, and then you only, let's see. I'd have to look. I don't, oh, actually, I have it right here. I don't remember if you need, oh, I didn't write it down. I don't remember if you need both outputs. You may only need the Q output, because I don't think the not Q is hooked to anything, although I could be wrong. So anyway, I'd have to double check the diagram, but it's a possibility you won't need both Q outputs, because just like, you know, we didn't need the carry out for the RCA for lab 4. I'm not sure for lab 5 you need both Q outputs, but we'll find out when we look at the diagram. Okay, but the key thing is, and this is what's new, and I just want to make sure I get the syntax right here, is that when you're doing a sequential circuit, like a flip-flop, you don't use always comb, right? Because remember, the comb stands for combinational, right? And we no longer have combinational now, since this is memory. So when you have a sequential circuit in System Verilog, you use an always FF block. Okay, so the always underscore FF. And then it's the @ symbol. Okay, the at, that's not a very good at symbol, but the at symbol. Now, this is where you either tell it to be rising edge or falling edge. Okay, in the parentheses, if it's rising edge, and you want to make it rising edge for lab 5, you do pause edge, and then there's a space, then CLK. Okay, so what this means is, see, since you put pause edge clock in the parentheses, that means whatever's in this always FF block is going to be evaluated at the time of the positive edge of the clock, which again, that's the rising edge. So this is going to, whatever you put here in the always FF, it's going to get evaluated at the time of every 0 to 1 transition of the clock. If you wanted this to be falling edge triggered, you would put neg edge instead of pause edge. Okay. All right, then it needs a begin. And we'll have an end down here for that begin. But now this is where you can put your, either an if statement or a case statement. I used an if. So, and in your if, what order you put your inputs is what's going to determine the precedence. Okay. And we want reset to have highest precedence, and then set, and then enable. So to do that, you have to put it in that order. So, I put if reset, okay, and this is going to make it active high. If I wanted it active low, like Ray asked earlier, I put an exclamation point in front of this reset. But we want our inputs in lab 5 to our flip-flop to be all active high. They're also all synchronous. Okay, but I'll explain how to do it asynchronous coming up here. So if reset, right? If reset is activated, if it's high, we want to assign Q 0. Okay, now here's another really important point. When you have an always FF block, you have to use the less than with the equal when you're assigning outputs. If you think back to an always comb, when you assigned an output, you just had an equal. Okay, but if you just use an equal in an always FF, or if you use a less than with an equal in an always comb, that's going to cause problems. Okay, and the reason being, and I have an example here. See, when you have the less than with the equal sign, that's called non-blocking. I'm not sure why they call it non-blocking, but that's the term they use. When it's just an equal, they call it blocking. But here's the difference between the two. If you have blocking, we'll start with blocking first. So this is, this is what you use with an always comb. Always. Okay, and this is what you use with an always FF. Always. Okay, so if you have the blocking, the equal sign, and first you assign B to A and then you assign C to B, well, C would equal A. Okay, because essentially what system parallel is going to do when it has this code, it's just going to generate a wire with A, B, and C on that same wire. And again, if you have circuits, if it's a connection called a node, it's all going to have the same voltage, so they'd all be equal. But if you do the non-blocking, A is not going to equal C if you do this. Because system Verilog, it doesn't take this and model it as a wire. It actually puts circuitry in between. So A, B, and C, they're not connected on the same wire. There's actually circuitry, that has to do with memory that's put in between. Okay. So, the gist of this is that you always have to make sure when it's an always FF that you're using the less than with the equal when you're assigning outputs. And when it's an always comb, you're using the equal sign. Okay. All right, but getting back to this, so if reset, this is going to happen. Else if set. Okay, what would we assign Q for set? Because what does set mean? When it's activated, what are we gonna make happen if set is activated? Yeah, Q equals 1. So you're just gonna set Q equal to 1. Else if enable. Now I can't remember in lab 5, I think instead of enable, I think we use enter. Okay, but whatever word we're using for enable, you would put next. So if we're not resetting and we're not setting, well then when we enable, when we enter, that's when we want Q to equal whatever's on the D input. Okay, so this would be Q assigned to D. Okay, so what would you think comes next? I have an if, and an else if, and an else if. Yeah, when you think we'd have an else, right? Because in an always comb, right, where you're doing prior to today, where we didn't want memory, we have to end in an else, right? But here, this is sequential. This is a flip-flop. We want memory. So if I'm not resetting, if I'm not setting, and I'm not entering, I just want the output to stay the same. I want to retain previous data. And in system Verilog, a way to get memory, a way to get storage is have an if statement without an else. So you wouldn't write an else here on purpose. Okay, so I'll come up here, right? So I'll put a comment, right? Remember comment in system Verilog, right? 2 slashes. See, no else because we want a latch. Right? Okay. So you can, maybe now you can see why or understand why the labs prior to lab 5 that had no memory, we didn't want you to have warnings with the latch, right? Because if you don't want memory, if you're doing combinational circuitry and you get a latch warning, that means that you probably have an error, you know, in your if statement or your case statement that's creating a latch that you don't want. And again, in this class, because the designs aren't overly complicated, or at least not as complicated as CP233, you know, you might be able to get by with additional circuitry and it still works, you know, the way you intended. But in CP233, that wouldn't happen. If you get any unintended latches in that class, your microprocessor is not going to work because it's going to throw off the timing. See, timing is more critical in that class than it is in this class. Okay, and then the last thing here you would need is just an end. You know, you gotta end this begin, and then an end module. Okay, but that's how you're gonna model one of the modules in lab 5. So let's see. I think the last thing I want to do here is just show you quickly the lab 5 diagram, because I mean, how many people, and I don't expect that many, if any, finish, but did anyone finish lab 4 prior to today? Oh, a few people have. That's impressive. Very good. Yeah, if you haven't, don't worry about it, because again, it's not due until after the midterm. It's due Friday of this week, so you still have more time. But if you have finished lab 4, once you're done with the activity, there's a small thing you could do for lab 5 if you wanted to. Okay, but lab 5 is not going to be due till a week from this Friday, so you got plenty of time. Didn't want to do lab 5 and use that time to study for the midterm. That would probably be wise. Just let me show you the diagram for lab 5. Okay, well, this is the video I was I was talking about that's on YouTube that explains the edge sensitivity of the flip-flop. But here is part of the diagram for, well, actually, let me show you this first. This is from a YouTube video, but it's the same lab 5. So here is lab 4. And for lab 5, what you're going to do is you're going to make modifications to lab 4. So you take your lab 4, you're not going to use your decoder in lab 5, so you can just get rid of that. You know, like create another project and just bring over, you know, these modules here. You don't need the decoder for lab 5, and you don't need this mux. I mean, you still need these muxes, but you don't need this one. Also, you don't need the neg output. There should be an X here for the neg output. We're not going to use an LED to indicate if the result is negative for lab 5. So you're going to take a portion of lab 4 that you already have, and then you're going to add this. Okay, and these are what are called registers. Okay, and we're going to talk about registers after the midterm on Thursday. See, a flip-flop can store a single bit. A register can store multiple bits. Right? If I just take multiple flip-flops and connect them up in a certain way, I get a register. Now, these two registers, even though they're labeled registers, they're really just a flip-flop, because this register is going to store the validity bit. It's going to store whatever's coming out of this output here. And this register, again, is really a flip-flop, because this register is just going to store this bit, okay, that we're calling the sign bit that was going to the neg output. Now, this is really a register, okay, because this is going to store the 4 bits that was going into your decoder. So coming out of this mux is going to go into this register, and it's going to store those 4 bits. Okay, so you got this storing 4 bits, this storing 1 bit, this storing 1 bit. And then this here, this is a module that Dr. Mealy designed. So you don't design this, we give you this. Now, I don't have the actual file, but I have a text file of the code. So you'll have to copy and paste the text into a file that's within this project. Couple of things to note when you do that. One is make sure you don't get any wraparound. Okay, sometimes people, when they do the copy paste, they'll get like a line that's, you know, on 2 lines instead of the 1 line originally it was on. You get like a wraparound, and that causes errors. The other thing is this code that Dr. Mealy wrote, it's in Verilog, not System Verilog. So when you choose the file to put the code in, make sure you choose Verilog and not System Verilog. Okay, but you can run Vivado with different files. Like you can have System Verilog with Verilog, and it will run fine. In fact, later on in the quarter, there's a couple of other Dr. Mealy modules that we'll use that were written in VHDL, which is a totally different language than Verilog. And again, it's okay to mix up languages. Vivado can handle that. Now, I'm going to go over in more detail on Thursday after the midterm about, you know, the circuitry here. But again, if you're done with lab 4 and you want to get a little head start on lab 5, you could do these registers that are just storing 1 bit. Okay, because I basically gave you the code. Okay, but this register that stores 4 bits, you'll know how to do that after or when I do the lecture on Thursday. And then you know, you could also, you know, copy and paste the text over for this module if you wanted to. But yeah, if you were able just to do the single bit register, again, lab 4 is the priority, but if you wanted to, that wouldn't take you much time. Okay, so now the activity is on Canvas. Like I said, there's 2 parts to it. That right here. So here's the PDF. This has, I think it's like 6 timing diagrams. So do that PDF first with the 6 timing diagrams, and it tells you how it's triggered, you know, synchronous or active low, and all that information. And then once you're done with that, then do the NOR latch. Okay, and again, the nor latch is just take this same diagram and put it in NOR gates instead of name gates, and just go through the same analysis and see that you can get this truth table. I took the truth table over here that you should get. Okay? All right, well, thank you for being patient today. I know it was a long lecture, but like I said, after the midterm, the lecture on Thursday won't be long at all. So do you have any questions before you get going? Okay, question?
Last Thursday's activity.
Right, yeah, thank you for reminding me. Remember, the activity Thursday was to demo to me that you can take an intermediate signal and show it on the timing diagram. And again, Dr. Benson shows how to do it in that troubleshooting video. So whenever you're ready to show me, just call me over. And I want to see that you actually bring it over and run it. Okay? Any other questions? And that that activity from Thursday, one I just explained, you have until the end of class Thursday to show me. So if you don't get to it today, just show me after the midterm on Thursday at some point. Okay?